Okay, hello everyone. So today we will start our new module in our F1 class. Before today's lecture, you already started two important reactive methods, the wall follow and the gap follow. So they are called reactive method because in both methods, you have no prior knowledge about the map or the position of your vehicle. And you only calculate your control output, the steer and the velocity based on the LiDAR scan. So both those methods are kind of reactive to only the current observation, and actually that's not enough for more robust and better performance in your race. That's why we are going to introduce localization and mapping and show how you can use them in a more advanced control, both geometric control or model predictive control method. So the lessons plan will be decomposed into 5 parts here. The first is the introduction to state estimation. And the second part, we will do a brief recap for the property and base rules. So you have the math tools to analyze the estimation of the distribution estimation problem. So the third part will be the recursive Bayes filter, and next follows the variants of Bayes filter like the Kalman filter family and also the particle filter. We will actually use the particle filter in our F1 car. So we will also have a tutorial of how to run the particle filter in ROS2 and last in your cars. Okay, and then the first part is the state estimation. In last week's lecture, you already started the dynamic kinematic model and dynamic model of the F1 car. We are using a very simple model, called the bicycle or the single track model. And you know that the system can be described as a series of first order original differential equations. So this is called the first order system. And then we can decide several state variables which can describe and determine the current state of the car. For example, in our F1 car, we know the state is the global position X and Y, the yaw angle, like the heading of the car, and then the velocity of the car. And also we have a system matrix and the input matrix to decide what the derivative of our state variables and decide how to calculate the next state of the vehicle based on the current state and the current input. And that's what's happening in the system. And to know that, we also have an output matrix, which basically measure using some sensor to measure the current state of our systems. And as you might see in the right side, we have two sensors. We basically have two sensors in our F1 car. The first one is an inertial measurement unit on the mask, which will give you the acceleration. And then there is a LiDAR, which will give you basically the range data, like the distance measurement from your position to any obstacles in your way. And that will be the two major sensors we used in our car. But in real world autonomous driving car, they have more complicated sensors. Like most important one is the GNSS for localization. And then they have a lot of cameras. The Tesla guys, they basically develop their whole autonomous driving systems based on a vision only solution. So they have cameras, and there's also radar or other distance measurement sensors. And in this case, we already know we can compute the system dynamic based on the current state and the control input. In our case, it's the steer and the velocity. In some other cars, it might be the velocity of the steer and the acceleration. And then a very important question is that how do we do the state estimation? Can we just use the input and current state to estimate the location of our car? Because in our case, that's the most important thing we want to know, our position of the car. Yeah. So when you do ROS2 topic echo odometry, when you already do these things all the times during the calibration. So when you do this, you will already see that under this odometry topic, it provides the velocity of the car, the current x, y, and there's a pulse. So there is a quaternion you can transfer into Euler angle and then the heading of the car. And the first question will be, can we just use them? Can we just use the this odometry message to calculate the next state? And actually, yes, you can. And this method is called dead reckoning, which is basically calculate the current position of the car by using only the previously position and incorporate the estimates of the current heading, speed, and the elapsed time. So it's a very simple idea, and it's actually used in navigation when in middle century, those guys, they use campers to traveling over the sea. They don't have a GNSS or GPS at that time. They can only rely on their current estimation of their position and then the directions and the speed to estimate what their next position will be in several days. So if you have the accurate value for the control input and the perfect kinematic model, then this is fine. Here we demonstrate a very simple example that your car will start at x equals to 1, and it has a speed of 1 meter per second. And then if you know that your car will exactly travel at 1 meter per second, and your car starts at 1, and after 1 second, it should be past like x equals to 2. So this is very simple, like forward Euler thing for your system dynamics, and you can be sure for that. But in reality, there's no free lunch. So there is always uncertainty in the measurement and system model. The uncertainty in the measurement and system model will create cumulative errors. Just let's recall the calibration you did and the parameters you tuned for the car. You know you need to adjust the speed to RPM gain, so the measurements under the odometry will be aligned with your with the distance that your car actually traveled in the real world. But you also see that no matter what kind of effort you put into that, you tune these parameters for several hours. At the end, you can still get a rough. It's still an estimation, and you might be accurately the numbers under the odometry might be accurate for the first few seconds, but let's say you traveled for 5 meters and the x under the odometry shows 5, also shows 5, linear x under the odometry also shows 5 meters. But as your car goes further away, then the estimation will become more and more inaccurate because of the cumulative error in these forward Euler things. So this is an existing problem, and we can definitely do better besides only using dead reckoning. So what we can do is that to incorporate this uncertainty in our state estimation, we no longer can just say that this is a deterministic problem, but we need to model it as a question to approximate a distribution of the position. So with this distribution, we can incorporate the uncertainty measurement in our state estimation problem. So we will know that how to balance between our different inaccurate measurements and there's some other inaccurate measurements and how to merge them to make it a better estimation. So that's why we need the state, we introduce this state estimation, and this estimation is actually, and what we are estimate here is a distribution of the position. Okay, so since we are talking about the distribution, and now we are actually talking about the distribution of our state variable. In our case, it's the localization and like the position of the car. We have to do a quick recap of the property and base rule. Those, yeah. So let's come to our second part. Okay, so the base rule. I believe you already see those formulas in a lot of other classes, like the learning to robotics or just a very basic machine learning to do the maximum likelihood estimation. So the idea behind any of this, like maximum likelihood estimation or maximum or other like complicated machine learning algorithms, is actually very straightforward idea of the conditional probability and how to update this conditional probability. So what the base rule saying is that if we have so first we define a conditional probability here. The chance of event B when event A has already happened is called probability of B, of event B given A. And the base rule, when I started this, I always find it easier to start from the left side, like the product side. So the probability of event A and event B happen together is equals to the probability of event A happening times when A is given, when A is happening, then what's the probability of event B also happens. So P of A and B is equals to P of A times P of B given A. And let's, it works on both sides. So you can also say that P of A and B is equal to P of B and times P of A given B. So based on those two equations, we can derive the formal formula of the base rule, which is the probability of B given A is equal to the probability of A and B divided by probability of A. And go one step further, we can see that in here, we can substitute the PAB with another P like of A given B times PB. So yeah, it takes time to read all the formulas, and up to this point, it's just like some manipulation of the formulas. But actually, for this base rule, the scientists have given this very interpretable meanings of this formula. So this formula is saying that if now B is our event that actually we care about, like let's say B is the state, the distribution of the state that we want to estimate here, then what? How do we measure the how do we know that A will help us to update the estimation of B? So here you can see that if A is already happened, or if we have some knowledge of A, so in this case, A is the evidence or observation, then we can say we can update the distribution of B. So the posterior distribution of B given A will equal to the likelihood, which is the likelihood of A times the prior, like if nothing happens, what's our prior knowledge of B, and then divided by the evidence, like what's the probability of A actually happened. So in this case, the prior is the probability distribution before the evidence is considered, and the likelihood is the probability of the evidence giving the brief. So as you may see in the maximum likelihood estimation, this term is used to present how much can we trust the belief. How much can we trust the prior in this case? And then we know the evidence is usually calculated as a normalization term, because here we need this posterior distribution to satisfy the property of a PDF of the probability density function. So this evidence here is usually calculated as a normalizing term. And then we can obtain our posterior distribution here, which is PB given A. And that's the base rule. And also what's the meaning of each term in the base rule. Okay. And then the second important concept in the probability is the law of total probability. And the idea here is that if you have a very complicated problem, then you want to decompose it so into several sub-problems that can be easily solved. So if you have an unknown problem, you always trying to fit it into something that you already know. That's also another reason why people prefer Gaussian distribution. So you see Gaussian distribution everywhere. They use the Gaussian distribution to fit the Gaussian mixture model. They use it in the Gaussian mixture model to fit data, or later you will see it is also used in the extended Kalman filter and the Kalman filter family, because it's easy to compute. So the idea here is just that we can decompose the problem to something that we already know, that is tractable here. So in discrete case, suppose B1 to Bk are mutually exclusive and exhaustive events in a sample space, then for any event A in the sample space, the probability of A is equal to all those intersections of event A with all the other events B here. It will be more easier to see this Venn graph. So you can see that the event A is actually decomposed into several intersections with the B1, B2, and B3, and then it's to recover the A, we just need to sum over all the parts that is take over by other B1, B2, and B3 here. Yes, and this is for the discrete case. In the continuous case, from discrete to continuous, in most of the case, we always just substitute the sum with an integral, so it will become continuous. And this is the same thing in the law of total probability. So if we want the probability of A, we can actually integral from minus infinity to infinity, and based on the parts, that is based on the intersections of A and any other event X, and which form the whole sample space here. So just as a reminder, the capital F is represents the cumulative distribution function, which is like f x is equal to the probability of x equal to this smaller x1, and the derivative of the CDF is the PDF, which is the probability density function. Yes, and that's the role of total probability in both discrete case and continuous case. Okay, and then now we basically have the tools, have the mathematical foundations of the law of total probability and of the Bayes rule. Then what we can do is that from this simple Bayes rule here, which only consider two events, so we want to update our estimation for event B, and then we only know event A here. But in the real world, we actually have a lot of more information than just one kind of information. And that's why we can actually expand this Bayes rule to incorporate more events here. So this will looks like just another mathematical manipulation here, and just some formulas. But if those C1 to Cn here are the historical information, then this is the formula of the recursive Bayes filter. If the C1 to Cn here is multiple sensor measurements at the same timestamp, we will actually get a sensor fusion, the format of the sensor fusion. So it all depends on what kind of information you want to consider, what kind of information you want to incorporate as your evidence. If you want to incorporate something as your evidence, just put them after the condition. You kind of update your state estimation condition on those things, and that's why we put them here. And then in our case, our state estimation is to approximate the distribution of the position, and then we can use the control input, use the dead reckoning as the prediction as the first step to update our estimation, and then we use the observation from the sensor data to do the correction. In this ways, we can merge two kind of information here and to get a better estimation in our state. So as the formula is demonstrated here, the current estimation x, at least as the current timestamp, will be conditioned on the current observation, the current control input, and also all the historical information here. And this one is our target. This one is what we want to estimate here. That's the distribution of our state x, given all the historical information. Yes, and that's what we will introduce in the next part, the recursive Bayes filter. Okay. So as you know, when we are introducing the historical information, we must have a series of like time varying data from the start to the current timestamp. And in our case, this is described as a hidden Markov model. I think you already heard of Markov model in some other classes before. And what's the differences between a Markov model and the hidden Markov model is actually with like simple tweaks in the definition. So first, let's define this hidden Markov model. We know our system have a state. The state will start at x1, and then we have a control input u1, and we will generate x2 based on condition on u1 and x1 here. And the Markov property is saying that the state x2 is only depending on x1 and u1 if we know both things, and the states of x3 is only depending on x2 and u2, regardless of what u1 and u1 and x1 are. So the state of the next timestamp only depends on the previous state and not the histories, because all the histories information is kind of squeezed to the current state. And that's the basic assumption in Markov model, that the history does not matter because the history information is already be compressed and be squeezed into the current state. And then what's the meaning of hidden here is that we cannot actually know the state x1, x2, x3 directly here, but what we know is the observation. For example, in our car, we for example, we want to know the velocity of the car, but it's not possible to. I wish there's some magical things that can just tell us the velocity of a car, but there is not. So what we have to do is that we use a sensor to measure the velocity of a car. In this case, this is called a sensor model. So the actual model here can be also called a motion model or a transition matrix, and they are just the similar terms that is saying that is describing the Markov property, that how can you transit from the previous state and the input. And then the sensor model basically given your current state, what is the observation will be like. So in our case, the goal of the recursive based filter is that if we start at timestamp t-1, then we need to advance the estimation of our state to time t. If we can do that from 0 to 1, then we can do that from 1 to timestamp 1 to timestamp 2, and just moving forward. And we can kind of have a tool to solve the state estimation problem. So that is the hidden Markov, that is the hidden Markov model. Basically, the most important thing is the actual model, and the second thing is the sensor model. And another way to interpret the actual model is that you can consider this as the likelihood of next state given the current control and the previous state. And for the observation, for the sensor model, you can consider it as the likelihood of the current observation given current state. And in the last few slides, you will see how those likelihood can be plugged in to the base rule to help update our belief here. So you already know the Markov property is the conditional independence. That is, if we want to estimate the likelihood of x3, we only need to know x2 and u2, as I mentioned before, because all the history information is kind of squeezed to x2 here. So that's why we can have a shortcut to simplify the lossy equations here. And after we have knowledge of this hidden Markov model, we can now enter the concept of the base filter. So we know our goal is to calculate the belief, like the estimation of the distribution of our state variable x. And in our case, the belief s of xt can be described as the probability of x at timestamp t condition on all the history informations, like from all the observation here and all the control input here. And excuse me. And because we are now trying to estimate the state at timestamp t, we can first break down the problem by conditioning on x t minus 1, because we want to make this problem tractable. In this case, we can start from something that we already know. So that's why we plug in xt minus 1 here using the law of total probability, because we know the current state can be like transit from all the, it's possible to be transit from all the previous states. So after we plug in the xt, we can write this intercontinuous version of the law of total probability, and then we will find out that after we apply the law of total probability, we have a recursive term here, because this one is actually the belief of the previous timestamp. So they have, you can see that they have the very, they have exactly the same format. It's just like here is xt and here is xt minus 1. So we find the recursive term here, which is good. And then we need to also deal with the first term. And for this one, we can just directly apply the Markov property, because since we have xt minus 1 here, then the observation and the control input in the previous timestamps are not important anymore. And it can actually just rely on the previous state and the current control input. And this one is the actual model, and this one is the posterior distribution of the previous timestamp. So this is the step 1 of the Bayes filter, like how to do a prediction with the control input, like we did in the dead ranking, because here we only incorporate one kind of information, which is the control input. So we get the actual model as the posterior distribution of previous timestamp. So this one is our belief after step 1. And then this one is actually called prior, because in step 2, we will update the posterior distribution based on the observation. So in Bayes rule, to calculate the posterior distribution, we need 3 terms. The first is the likelihood, the second is the prior, and the third one is the evidence, which is actually usually calculated as the normalization term. So after we apply Bayes rule here, we know that our goal here is to incorporate the information of the observation at timestamp t. So after we apply Bayes rule, like based on the observation t, we can have this term here, and then for this equation, we can apply the Markov property again on the first term, because the second term is just the prior that we calculate from step 1, and then after we apply the Markov property, we get the equation of the sensor model, and then the formula is look very clear here, that just the sensor model, which is the likelihood of the observation given the current estimation of the state, and then the prior distribution, and then this one is just the normalization term that we can use to normalize the this equation, so we can get a valid probability density function. So those are the 2 steps of the Bayes filter. The first incorporates the control input to do a prediction. We said this is prediction because it's kind of predict what will be the next state based on the previous state and the control input. And then secondly, we incorporate the information of the observation. So we do a correction here. Let's say, we have some noise in our dead reckoning in our first step, and then we can still correct it with our observation from the sensor data. So those are the two steps. Those are the formulas. But in the real world, when we want to use this phase filter, you will see that it does not it can be only, so the naive version of phase filter can basically can only be used for some simple discrete case, like you have a very clear transition matrix of this actual model, and then you have very simple expression of the sensor model. That's because if your conditional probability here is complicated distribution, then you need to do this multiplication and even integration for two might be very complicated probability distributions. And then you need to do the same thing in the correction step. So when you calculate, so the math is good, but when you trying to calculate those things, you will see that your distribution become more and more messy, and you cannot use a very neat numerical tool to solve that, because you can you have a very complicated functions, and you cannot easily sample from your distribution. So that's why in practice we actually use a lot of variants of the Bayes filter. So the first one, we meet our friend again, the Gaussian distribution. Basically, to solve this problem here, we just assume every probability we will deal with is a Gaussian distribution. Because Gaussian distribution is very good, it has a property that if two sets of the variables are both Gaussian, then the conditional distribution of one set condition on another set is also Gaussian. And then it is the same for the joint distribution. So if we have a Gaussian random variables x and y, then the joint distribution of x, y, the conditional distribution of x given y of y given x, and also the linear combination of like kx plus c or ky plus c, they are all Gaussian. So you are still in the field of dealing the Gaussian distributions, which is a good thing and easy, and we like easy things. So that's why we choose Gaussian distribution. Also because it's self-conjugate. So if we have a Gaussian likelihood function and we have a Gaussian prior, then we will also have a Gaussian posterior. Basically, the first one assure that in our prediction step we'll have a Gaussian distribution, and the second one assure that in our correction step, after we apply the Bayes rule, our distribution is still Gaussian. So in this case, our distribution is always Gaussian. It's Gaussian everywhere, and we don't have to maintain the PDF itself, because for a Gaussian distribution, to describe a Gaussian distribution, the mean, like the expectation, the average, the expectation vector, and the covariance matrix are enough. So we are actually just updating the expectation, the mean, and then the covariance. Then we can describe this Gaussian distribution and sample from that. Okay, so when we assume all the distributions are Gaussian, then we have the Kalman filter family. The first one is Kalman filter just for linear dynamics, linear system. And then if the dynamic function is nonlinear, so actually in our single track bicycle model for the F1 tens, it's nonlinear because you have the cosine sine term in there. But we can still use that. It's called extended Kalman filter. Basically, it's to tailor expansion in your dynamics to get a linearization form of your dynamics. And sometimes because the linearization itself cause some problem because it cannot it's only good when you have a very small step, and then you will be far away from this linear expansion here. So we also have an unscented Kalman filter, which is not using the linearization itself, but combine the idea of a sample-based method that use several sampled target point to represent the dynamics in the prediction part. So instead of the simple linearization, and that's the but all the Kalman filters assume that your belief that your distribution of your state itself is Gaussian. The only difference is that how they deal with the dynamics, if the dynamics is linear or it's approximated linear, or I use some sample-based method to estimate it. Yes. So another thing is that if we know the sampling-based method is actually very powerful because it can be shaped to do anything you want, then the next step will be, what if we just use this sample-based method to represent our goal here, the distribution of the state variable here. So this one is called the particle filter. It's called particle filter because in this case you are no longer maintaining the PDF or or in Kalman filter's case, the expectation and the covariance matrix itself, but you are maintaining a lot of particles, and each particle is a sample from an unknown distribution, and this distribution is your state estimation, your estimated distribution of the state. So in particle filter, you are maintaining all the particles so that you don't have to calculate the PDF itself, but you can just propagate the dynamic and the dynamics to the particle to predict their next state, and then use the scan matching methods to correct your state estimation. So this particle filter is actually very powerful, and it can solve some problem that cannot be solved by the Kalman filter family, and we will see that in next lecture. And for now, we can start with a very intuitive example of the Kalman filter, just to better understand the idea of how this filtering actually works. So first, in this example is a 1D example, and then our goal here is the state we want to estimate here is the position of the car. It's just the 1D position of the car. We know that we have a pole here to measure the distance between itself and another pole on a car. So the observation is the distance measurement given by the sensor, and then we know that for the sensor itself, it has some true measurements accuracy or the bias between the measurement and the true value. And then we also have a measurements precision, which model the uncertainty of the measurement. So basically, if we do multiple measurements, then we will have multiple different results, but not the same result every time, but the different result based on the Gaussian noise assumption. So that's our observation. And our assumption, recall our assumption for the Kalman filter is that both the state and the observation here follows the Gaussian distribution. Okay, so we have a Gaussian sensor model, and then we model our state estimation as also as a Gaussian distribution. And then the step of the Kalman filter can be decomposed into several steps. The first one is the initial position. So the initial knowledge of the system at time t equals to 0 is demonstrated here, and the arrow pointing to the right represents the initial velocity of the car. So basically, this is x0 is our start point, initial position. And then the first step is that we can do the prediction with the control input. So the prediction of the location of the car, it depends on of the car at next timestamp. In our case, the t equals 1, depends on the previous state here, previous position, and the control input. And you can see now the level of uncertainty is increased in this PDF here. So it's more, it gets expanded because because our state transition has some uncertainties. If your car is here, then it will be after plug in the velocity, plug in the dynamic model, and then you will get a new position. And then if your car is here, it will also get another new position. So because we have uncertainty in our the transition model, the actual model, then our uncertainty of the state estimation also increase, and we have lower confidence of the exact position of the car. And then the next step will be correction with the observation. So after the prediction, we have uncertainty. We have one distribution that is called the prior distribution, and then we have the evidence here. So the measurement itself, we know it's another Gaussian distribution, and we see that between the true, we will call it the true position for now, and there is always the bias between the true position and the mean of the measurements. So this is the bias or the accuracy of the sensor. So our sensor is also not perfect, and that's why we also need to model it as a Gaussian distribution. So the uncertainty of that noisy measurements is represented by this blue Gaussian here. And then now we have two distribution, the prior distribution and the distribution from the measurements. Then we can, what we do is that we just combine those two distributions together. If you look into the details of Kalman filter, you know in this step, they actually calculate the Kalman gain, like a weighted, it's calculating a weighted sum of the prior distribution and the measurement to get the posterior distribution. But the intuition here is just that we are merging two distributions together based on how uncertain they are and what's the differences between them. So a very I would want to point out here is that if you have a very uncertain measurements. Like if your measurement is way diffused from the expectation, it just means that you are not very confident of your measurement. And then the weight assigned for this measurement distribution will be small. And then when you combine those two distributions. So that's how the uncertainty or the covariance matrix of the Gaussian distribution is affecting how you combine those two distributions together. And now you have an updated posterior distribution of your of the position of the car. So that's basically the different steps of the Kalman filter. And here we also have another example. So the blue line is the true trajectory here, and the black line is the dead directing trajectory that only relies on the forward Euler, the previous state and the velocity. And the green points are the observation. Then the red line is the estimated trajectory with standard Kalman filter. And the ellipse here is the estimated covariance matrix of the Kalman filter. So you can see that at the beginning, the black line is actually quite aligned with the blue line because the cumulative error is not large. But as time goes by, the black line gets deviated from the true trajectory. But because we have those good observations, although the observation itself is noise, but since we also combine the knowledge of the dynamics, and we are not, we have benefits both from the dynamic model and the noise, but kind of accurate observation. So the red line of the EKF actually is very good, and it's quite aligned with the true trajectory. So that's something that's good about the EKF, but it can also fail in some cases because in some cases we will have a non-Gaussian. So in the previous cases, the noise is Gaussian, then it's very good. But sometimes we have non-Gaussian noise. So as you can see here, this one is the observation from the GNSS, and this data we actually collected from another project in our lab is called autonomous go-kart. It's a larger size of car that you can actually sit in and drive it along the Pennsylvania. But the problem here with the GNSS is that it has noise, but the noise is not nicely Gaussian distributed along the true value, but it's deviated in only one direction. So as you can see, the position observation here is that it's kind of jumped suddenly from here to here. And with EKF, we know that this measurement is not very accurate here, and we need to consider the dynamic of the systems. So when the estimation is way far away from the true trajectory, the EKF knows that based on the covariance matrix that this currently GNSS is noise and it's uncertain about itself, so it will not follow it. But since it's still a distribution that the estimation want to incorporate, so the EKF will still go that way. It will be slower because it will try to respect the dynamic more instead of the observation here. So it will gradually go to the wrong ways, but because the non-Gaussian noise, it will still in the wrong direction until the GNSS is confident again, until it gets back. So in this case, the EKF, because the noise is non-Gaussian, the EKF can have some kind of smoothing or reducing the error here, but it still cannot solve the problem. So in this case, what we end up with is that because the GNSS is reliable most of the time, it just kind of jumps in time to time in some time points. So, but when it jumps, it will give us a high covariance matrix, means that it has high uncertainty and it's not very confident with its current measurement. So whenever there's a high uncertainty in GNSS, we just go back to that ranking. So we kind of fully abandon the observation, the correction step, but more relies on the dynamic model to fill this gap. So that's kind of tricky, but that's why we have this practice problem of the Kalman filter. So in engineer case, sometimes you just need to do some ad hoc logic and solve it in a tricky way, I think. So because there are problems with this particle Kalman filter, it requires that the noise should be Gaussian and anything. So the thing we actually used in the car is called particle filter, and we will introduce that in the next lecture. Yes, and that will be all the content for today. And if you have any questions, I will be glad to take that after class, so during the office hour. Okay.